Hi there and welcome to video 4 for modelling. This is the video on modelling with vectors. So we've looked a little bit so far at how we build a model, what assumptions we might make and what implications they might have. Now quite often when we're working with mechanics we're working with vectors, as we've already kind of looked at previously in the course so far. Now we need to have a real sense of what vector and scalar quantities are. We will represent a series of physical quantities with vector notation, especially when they are themselves vector quantities. And we're going to have to be able to kind of solve problems with those vectors. Now, we know that a vector has magnitude and directions. That means any vector quantity also has a magnitude and a direction. A scalar quantity will have only magnitude. Now, we need to know what the vector quantity of a kind of a scalar quantity is, or what the pairs of them are. So vector quantity of distance is displacement, the vector quantity of speed is velocity. Acceleration we don't really distinguish, but will be shown through the vector quantity, and force is the same. So if we're given a vector as the force, then we know we're dealing with a vector quantity there. Those are our four main quantities, or four main kind of physical characteristics we'll be looking at as we go through the mechanics. So displacement, velocity, acceleration and force for vector quantities, and then distance, speed, acceleration and force for scalar quantities. So one key skill, and this is something that we've done before, is being able to find a scalar equivalent of a vector quantity, and that's by using the magnitude of that vector. So if I have a velocity v, which is 3i minus 2j meters per second, I can find the speed, which you can see I've used the magnitude of the vector v to show me what the speed is. I can use Pythagoras to find that magnitude of the speed, magnitude of the velocity, so the speed, as root 13 meters per second. Another key skill, and again something that we've done before, is being able to find a direction that a vector is acting in using trigonometry. So for instance, if I want to find the angle the acceleration a makes with the vector j, I've got this vector a, which is negative 2i plus 3j meters per second squared. I will always draw a diagram to do these questions. Trying to do them without will quite often lead to us making a silly mistake with our trigonometric functions. So here is a kind of an idea of what this vector looks like, negative 2i plus 3j, and that's my vector A. This is the vector j. J just goes up one step. So the vector j goes up, and so I'm looking for this angle here, this angle theta. To do that, I'm going to complete my triangle and then think about what my two side lengths here are. I've got 2 across because it's negative 2i. I've got 3 up because it's 3j. Now that triangle, simple right angle triangle, and I can use that to find theta. So I know that the inverse tangent of 2 over 3 will give me theta, because tan is the opposite divided by the adjacent. That gives me 33.7 degrees. Key thing with this, always draw the diagram. If we do that, we'll get those right every single time. We also will occasionally get problems in using vectors. We've kind of done a couple of these when we did the vectors unit earlier this year. And the key thing again with these is always make sure that we are drawing a diagram. I've got a cyclist who starts at the point B with the position vector B, which equals 5a plus 7j. 5i plus 7j, and rides to a point C, which has a position vector C equals 7i minus 8j. So I want to calculate the displacement of the cyclist at point C. One key thing to notice here is it asks me to calculate the displacement here. Okay, so I know my answer will be a vector, because displacement is a vector. If that's a distance, I might well have to do an extra step. Okay, so always we're just going to be checking what we're going to give our answer in what final form. But again, the key thing is a diagram here. A cyclist starts at the point B with the position vector B equals 5i plus 7j. So that is my vector B. So starts there and rides the point C, which has this position vector C, which is 7i minus 8j. So my path that my cyclist rides along is B to C here. Okay, so I want to calculate the displacement of the cyclist at point C. Now displacement is the linear distance that's been travelled from a starting point. So I can find that using the vectors. I can find the vector BC, and that will give me, and I can find that using BO plus OC. That's BO is the vector negative B, I'm going the wrong way down this vector, plus C. That is this, and then this is just some expanding and simplifying, and I get 2i minus 15j. So the displacement at that point is 2i minus 15j. If this was asking for the distance of the point C from B, we could then find the magnitude of this vector just to solve that fit finally. But here we're asked for the displacement, and so we're finished using this, and we can leave that as our answer. So the displacement BC equals 2i minus 15j. One last thing we're going to look at is slightly complicated initially, and I'm going to show you this now, and it will lead very nicely onto our next unit, which will be starting after the mix exercise, which is the next sheet after this one. But this is where we might model something using vector quantity, which is one-dimensional. That is, you can have a positive or a negative direction. So we're not using two dimensions like I and j, we're just using one dimension as positive or negative. And we'll give you a sense of what that looks like now, and we really have to kind of be thinking about what is happening at each stage of this motion. So let's have a particle that starts at a velocity of 10 meters per second at a point A, and it decelerates uniformly to a point C, where it instantaneously stops and returns to the point A. Some key terminology here. We've got uniform deceleration. We'll be talking more about this in the next unit, but uniform deceleration means that the magnitude of that acceleration is fixed. It is not changing itself. So the acceleration throughout this process will be the same. And we've got a uniform deceleration, so we know that the thing is going to be getting slower, and that's implied by the fact that it's then going to instantaneously stop at point C before it returns to point A. So I'm going to draw a diagram of this to see what's happening at each individual point, and I'm going to model the displacement, the velocity, and the acceleration at each time. So here I've got A, B, and C. I've put B in the middle there because it's an interesting way of us looking at this motion. But if I've got this particle A, and I'm going to define one particular direction as positive, this is something I can do myself. It does not change my outcome. It will not change my answers, but it may well be kind of useful for me to define a particular direction as positive. This particle starts moving in this direction, and so I've defined it as positive. So it starts at a velocity of 10 meters per second at point A, and so I've defined this way as positive. So at the point A, the displacement is 0. That's the distance from point A is 0. The velocity is 10 meters per second, and I'm told that in the question. And I know that my acceleration must be negative. Now I know that, and this can be slightly confusing, but I know my acceleration is negative because I'm decelerating. Okay, so deceleration is where I have an acceleration against the motion. Now, importantly, it won't always be negative. The key thing here is if my velocity was negative, my acceleration would be positive. What I want when I have deceleration is the acceleration is going against the velocity. And each of these are vectors. Okay, so what I'm saying is my acceleration vector is pointing towards A, whereas my velocity vector at the beginning here is pointing away from A towards C. At point B, I've got a positive displacement, I've got a positive velocity, and I've got a negative acceleration. Key thing is this positive velocity will be less than 10 because I will have decelerated between A and B. Okay, so I still have this uniform acceleration which has the same value. This will be the same value, the same negative value, but my velocity here will have changed. It will have got less, but it will still be positive because I'm still moving towards C at this point. So even though this has got smaller, it does not mean that my velocity is now negative. And my displacement here is positive because I have moved some distance in the positive direction away from my starting point A. Then when I get to point C, I'm going to have an even bigger positive displacement. This will be the maximum displacement as I get to C. My velocity is now 0 meters per second because I'm told it instantaneously stops at point C. But my acceleration is still negative. My acceleration vector is still pointing towards A. So it's still trying to push this. I'm still accelerating here towards A. And what's happened is this acceleration vector has kind of taken the speed, the velocity away from this particle and stopped it at C. And that acceleration will then make that particle accelerate towards A. So as it starts returning, I'll be back at B and I'll have the same displacement as I did before when I was at the point B. That displacement is still positive, even though I'm moving back towards A, because the distance from A to B is still in the positive direction. I will have a negative velocity at this point. I'm moving back towards A, and so at this point my velocity vector is pointing in the opposite direction to my positive, to the way I've defined positive. So my velocity vector is negative, and my acceleration is also negative. Now, when I have my velocity and acceleration vectors both in the same direction, that tells me that the magnitude of this velocity must be increasing. I am getting quicker as I move back to the point A, because this acceleration is negative. And then finally, as I return to A, I'll have a displacement of 0 meters. Displacement is always measured from the starting point. I have a velocity of negative 10 meters per second, okay? Because this acceleration is uniform, I'll have gone out, stopped, and come back, and got a speed of a velocity of negative 10 meters per second, and I'll have still that absolutely the uniform negative acceleration. Now, that may well be a little confusing. I would encourage you to rewatch that if that's useful for you. We will look at this again. The key thing here to understand is to be thinking about these positive and negative displacement, velocity, and acceleration vectors, and be thinking about the way in which they interact. Some of the most common mistakes are where we think, when we start coming back from C, that my displacement will now be negative because I'm moving in a negative direction. The displacement at all times is going to be measured from the starting point. I also need to be aware that sometimes my velocity and acceleration vectors will be going in opposite directions. That means that the magnitude of the velocity will be reducing. If they're both in the same direction, either they are both positive or they are both negative, that the magnitude of the velocity will be increasing. Lastly, I just want to make it really clear that actually all that would happen if I changed this direction, if I said that actually pointing towards A was positive, that I just change all of the signs of everything I've done so far today, everything I've done from point A, B and C. And actually it would not change any of the values. It's an arbitrary choice I make. It has implications for my calculations, and if I'm not consistent, then I'll get the wrong answer. But choosing a direction is completely up to the person doing the calculation. As we move into the next unit, we'll look more and more at this, and it will become more and more important that we're consistent when we're doing that calculation. But just to introduce this to you now, so I've got a one-dimensional vectorial problem. I've got positive and negative speeds, positive and negative velocities and positive and negative accelerations. As long as I am consistent, I will always get the right answer. Any questions, by all means let us know. Otherwise, please move on to the pre-quiz and then have a look at the sheet.